strong covalent type interaction above 5 kPa. Okay, so this is represent the attractive force inside your system. So that's the mean state frequency. That's the second step that you got here, right? This is our picture, second step. And then finally, what about E, the desorption rate that you got here? The desorption rate should be equal to, right? I'll make it a simple argument, should be equal to the population, the surface population of your particle. Let's say they stuck somehow, divided by this mean surface rate lifetime. Okay, because that's how often it dissolves, right? Because it's the number density on the surface divided by the surface lifetime. So that's it. So once you got it written like that, then you say, okay, so that's my complete picture. Now I say at equilibrium, my absorption rate, right, which is my impinging rate, must be equal to desorption rate because they have to have reached some sort of dynamic equilibrium. So you make I equal to E, and then you come up with a expression which I call a fundamental kinetic equation for absorption equilibrium. That's kind of a long name. Think of it as a fundamental kinetic equations for this type of simple picture that you got. You write it in this way because you say E is equal to I, and so you can write N here is tau times E, right? And because E is equal to I, so you have tau times I. Okay, so it's a simple algebra conversion. And N here, of course, is my surface concentration, right? Kind of like I'm approaching my idea of coverage, right? The amount of particle absorbed on there. So that my surface concentration is my surface lifetime, right? Times the impinging rate. Okay, if you don't remember anything else, I hope you remember this simple concept that surface concentration should be equal to the surface lifetime of that particle times the impinging rate. So that's the basic idea. So this is basic fundamental idea that people should know, right? That's it. And then there's little detail. Okay, the detail is that okay, this because of this this expression and my expression of my detail of my surface lifetime, I can expand this concept into some equation that the surface concentration should be proportional to the pressure, right? And some sort of Arrhenius type equation, E to the delta X desorption. So the other thing that if you want to go into detail, it should be the surface concentration should be proportional to the pressure that you are using the particle beam to throw at the surface, right? Which again is reasonable because the higher the pressure, the higher the surface concentration you should expect. And furthermore, the higher the desorption energy, right? In other words, the more energy you take to desorb your absorbate, the higher, again, the higher the surface concentration as well, because this is kind of an exponential decay, Arrhenius type equation, exponential dependent E to the delta X desorption divided by KT or RT, depending on how you write this. Okay, so that's, I think, ignoring all the derivation, I think we can see, right, we can see the physics, the chemistry involved of your surface concentration proportional to pressure and proportional E to the delta X desorption, right? That's the basic concept that we have. And one of the kicker in all this, people who are looking at absorption idea is that this delta X desorption may sometimes depending on the surface concentration itself. Okay, so because this desorption energy obviously depends on how many particles you have in there, because now you have nearest neighbor interaction again, right? So you have fine interaction. If you have zero coverage initially, the interaction is straightforward because you just have the particle interacting with your surface element. as you have more and more coverage, more and more atom on the surface, you have to consider now the interaction between particle absorbed on the surface. And that's why sometimes delta H desorption depends on this surface concentration. And again, this leads to a little bit of complication, which we don't want to talk about. But that's it. Okay, so I hope you see this. I hope you see it. We may not be able to derive it, but I hope you see the basic concept, which is reasonable in terms of surface concentration, surface lifetime, and impinging rate. Okay, next, we use this kinetic equation for our beloved Langmuir model, right? Which is the model we use to look at chemi-absorption, right? This is the fundamental thing. And whether we can derive this Langmuir picture that we started at the beginning of this lecture. And the Langmuir model assumes a couple of things, and I hope people remember this. What is the basic physics involved? Langmuir model, Erwin Langmuir said the following thing. Right? This is why he's a Nobel winner, because he come up with some simple idea, and you can come up with some concept of understanding chemi-absorption. And he was awarded Nobel Prize in the 50s because of this contribution. So he said the following thing. He said, okay, and it's all rather simple, right, at the time, but it's powerful assumption. So he assumed the atom, this absorbate particle, are held at certain site. Okay, so you picture your surface, right? Your surface had many possible geometry, and these create absorption site. And he said, okay, you may have many different types of absorption site, but we assume your absorbate only interact with certain sites. So there's a specific absorption site that you have in mind. Then, because they are all absorbing in the same type specific site, is delta H of desorption, right, ought to be the same for all these sites, okay, for all these absorption sites. Okay. So that's a fundamental change, fundamental idea that if you want to carry the Langmuir picture in the first general sense, you can assume all the absorption sites have the same desorption energy. In other words, all the absorption sites are equivalent. And he said, which is very fundamental, he said that once the molecule absorbs, the particle absorbs, it cannot move anymore. It cannot, there's no surface diffusion process, no motion of an atom on your surface, right? Once it's stuck, that's it. It cannot move, it's trapped in that site. It cannot move jump from one site to another. And that's why, okay, so it's this assumption that often associate Langmuir model to chemi-absorption, because chemi-absorption above 5 kcal per mole is very strong. It's stuck, you look at the mean stay lifetime that we just talked about, is over 100 seconds and so forth. Okay? And furthermore, this is not a physi-absorption, not a condensation type model, because he said one last thing, which is that once the site is occupied, you can't put another atom on top. Okay? In other words, what does that mean, really? It means that your particle, your atom, your absorbate, interact much strongly with the surface atom rather than between itself, right? Because it is strongly interacting between itself, then you would expect, okay, your absorbate may interact with another incoming particle and form sort of a dimer or trimer kind of thing. But he said, no, you cannot have that. The only strong interaction between absorbate atom and your surface atom. Okay? So no two absorbate can absorb on the same site. Once the site is occupied, that's it. The other atom cannot come on the same site. Okay. So again, so as you can see, what is the best picture for this? The best picture for this is really chemi-absorption right, of sort of a non-interacting particle in some way is sort of